And get started. Thanks for that, Iris. Welcome back, everyone, to day one of IGSS. I think we've had some really great talks today. It's the last session of the day today. And I'd like to invite Juan Salamanca and Daniela Delgado from the University of Illinois to talk about inverse generated identity from interactions in self-organizing groups. Juan, if you want to share your screen and get started.
Okay.
Thank you. Over to you.
Give me a second.
Sure. Excellent.
Okay. I think you can see my slides.
Yes, that looks great.
All right. Well, thank you very much for the opportunity to share our work. My name is Juan Salamanca, and I'm presenting with Daniela Delgado. I am from the School of Art and Design at the University of Illinois. Daniela is a doctoral student at the School of Informatics. So the work we are presenting today is like early findings on a branch of our research and the study of how the built environment, and more specifically talking about artifacts, participating in social life. And the overall goal of this research is to design socially apt artifacts that smooth action flows in unplanned interactions. When we say unplanned interactions, we're talking about pedestrians on streets. It's like a represented case of unorchestrated social interactions, so people don't like prearrange themselves before to walk on the streets, just something that emerged as people walk on streets. And in walking on the streets, the walkers execute a program of action that brings them into trajectory negotiations that may respond to people adjusting themselves, their inertia, their action flow, their rhythms, depending on how many people they encounter, and also the variation of the action flow that people execute on the crosswalks permeates the network of all the walkers on the street. So when the two trajectories, conflicted trajectories, are negotiated, they are essentially, that negotiation is the contrast between expectations of two walkers, or two pedestrians. So I expect people to go on the left, people go on the right, but others also have expectations on my actions. And that kind of like adjustment of actions, we call that like a social viscosity, because action flows are constantly accelerating, decelerating, and all that flow, or that action flow as an aggregated, we name that as a viscosity. So this is not changing. So today we are like presenting here our early attempt to measure and analyze social viscosity. And in doing that, we found that the theory of identity formation, one of the theories of the theory of formation matches our vision of how this social viscosity works. So we build an agent-based model and to analyze viscosity, and then we implement reinforcement learning in some of the agents, trying to learn how to sort out the navigation in the space. So technically, we define social viscosity as the resistance to action flow by actors that completely enact the problem of action. And by contrasting expectations of other people's actions and their realization of the social situation is how we measure social viscosity. And the magnitude of that viscosity is essentially the magnitude of the adaptation I need to do in order to sort out conflicts with others. Our case is a simple model of color, or the analysis of color proximity. And what we're doing here is like creating an agent-based model based on observations of a participatory simulation. Our participatory simulation is a replication of Shepard and Cooper's analysis of how mental models on color proximity. What Shepard and Cooper demonstrate is that we have like Newton's color wheel as a model to organize colors, and we can either organize those colors if we perceive them, like visually looking at those colors, or if we mentally think of those colors. So I can think of orange and red and kind of have I can create a like mental proximity between those two hues, and that allows us to organize color proximities. So what we did is essentially we recreate the Shepard and Cooper's experiment, but instead of like or people organizing samples of colors, we asked people to impersonate a color. So every single agent was, or every single participant was given a color, and we asked them to organize themselves, basically being close to those that are similar to each other and being far away from those that are different. And as you see on the screen, the evolution of the participatory simulation, people initially create cliques or small groups, and then they select opening and connecting those cliques. And at the end, we found that people organize themselves by the Newton's color wheel. So it's again a demonstration of like that mental model that is like embedded or in our brains. So we made a custom-based, web-based multi-agent model to analyze to replicate our observations. In the simulation, we have perception, cognition, action cycle. So it's basically those 3 steps. People first perceive the agents in a given radius or proximity. That's one of the parameters. You can choose the radius of action. So and you perceive their colors, and when you have that notion of colors and distances, physical distance, you can estimate an ideal proximity to each one of your interactors, and then you execute an action. And then you are contrasting the expectation of how you want the world to be against how the world is enacted. So each agent has 2 mental models. One of them is the color proximity, and the other one is the spatial proximity. And you can convert units from one to the other. But spatial proximity is essentially a range between what agents decided is too close or too far. And the color proximity, the color model is a sequence of, a discrete sequence of hues, starting from red and finishing on purple. But this sequence, based on like the color wheel, it's connected. Both ends are connected. So red is close to purple. So the model is a circular arrangement. But there are also the possibility to represent the model as a sequence of colors, starting in red and finishing in purple. And that's a different geometrical arrangement of elements. So we parallel this with identity control theory in the sense that agents know one color, which is what identifies themselves as being red or being green or being blue. And that's the notion of the self concept is associated to being one hue. And there is also a social concept of how people interpret where I am in that social organization. So being red has a meaning in that arrangement of colors. The meaning is being close to orange, close to purple, and far away from red, for green, sorry. We here exemplified two different agents, red and yellow, and red may have a different tolerance to proximity than yellow. For red, one step away from yellow is okay. From yellow, that is too close. So the notion of tolerance to proximity for the perspective of red is too close. So from the perspective of two different agents, the idea of being close or far away, it's not exactly the same. We call that the tolerance, and the tolerance to being the imperfect action. In this slide, we show, and on the left, the result of a convergence after a number of ticks or time steps. And the upper row, we see the visualization of how agents are estimated distances. And as you go progressively to the right, the third hit shows of distances. In the lower row, it's showing that not all the agents may interact with each other. So because of the radius, the matrix is incomplete. But as they converge, the matrix progressively completes all the tiles. And this is a representation of the social viscosity. The curve on the left represents like progressively the conversion and the closer to the ideal proximities, the lower the viscosity, because the expectations of other people being in where I intend them to be are less are matching what is observed in reality in the actual simulation. And the heat maps here represent that discrepancy between the expected proximity and the actual proximity. And as you see, like the colors are like kind of attenuating in the progression. So that is the original model. But when we start realizing that this model may have, it requires that people know the color wheel, and we start wondering, well, is the neutron color wheel something that is phylogenetically inherited, or is something that we acquire by Western education? There are some research in the linguistics of colors, and some origin groups around the world don't have names for some of the common Western colors. So we're still like wondering, what if we insert here an agent that doesn't know the color model and starts like inferring the color model or developing a color model from interactions? So Daniela is going to present that development.
Hello. So as we mentioned before, identity can be a key element for self-organizing group, but identity is not only the characteristics internal of the individuals, but also how it interacts with other social agents. So the social selves describe the role of individuals in a social situation, and it's fundamental part of the identity. Identity control theory suggests a continuous adjustment of the individual's identity to the interaction with others. Then one's identity not only determines how we perceive and relate with others, but these relationships and interactions reinforce the individual's self-concept. So Therefore, a newcomer totally unaware of the social norms of the context ignores also a big part of its social identity. In our color metaphor, it ignores its position in the color palette. Thus, it relies on its ongoing experience to learn the model and that encapsulates the social norms and to develop its own identity. Okay, so in order to represent this, we added a new agent, which ignores the color model that guides others' actions. And this new agent will construct its identity while interacting with others. At the very beginning, after perceiving the distances of others in the space, the agent randomly selects a model from a collection of pre-generated possible models. These are represented as color permutations. So then the agent uses that model for the cognition, and where it translates the color order in desired distance. And after that, it takes action, moving closer or further to the other agents. So then the agent perceives the work again. And in this perception allows the agent to evaluate the previous model it selected. And by comparing the expected behavior to the actual movement of other agents. So if we see in the previous time step T0, the model suggested that violet was the closest color to red, and green was the furthest. However, when the agent moved, in the next time step, it discovered violet goes away and the green comes closer. That means that the previous model used wasn't good, so it's penalized, and a new model with a higher quality can be chosen. With this model, the agent goes to the cognition and the action phase again and again until the agent finds a model that makes a good enough explanation of the work. So to evaluate the models and to allow this identity reinforcement process, we use a simplification of the Q-learning equation. So each time the same model is evaluated, its quality value is updated, summing the previous value to the product of the learning rate and the decreasing factor, divided by the sum of the decreasing factor and the number of times this model have been explored before. All these multiplies the reward that depends on if the prediction, if the prediction was successful or not. So if the prediction was successful, the model predicted successfully the behavior of the agents, then the reward will be positive and it will be negative in the other if it wasn't a good predictor. So we added this decreasing factor in order to force the learning process to converge. And then this recursive algorithm don't assure learning the correct model by the agent, so it only assures that this model, the selected model, is good enough for the experience the agent had in the social space. So now we will see some simulations.
So these screenshots are showing a very simple model just to simplify how it works. Here the learning agent is a yellow one. It at the beginning doesn't have any idea of the color mental model. It only just knows that it's yellow, and as from the interactions, it develops its own color wheel. Now you see here on the right, this is the actual configuration that is 5 out of 6 agents have the neutron color wheel, and as you see, the result is again the neutron color wheel. So it means that even though yellow doesn't really know the color wheel, it is able to act in a way that is accepted by the social group. But the order of colors here on the left I don't know if I can see my pointer. Yeah, see, so here this yellow is supposed to be one step from green, according to this, one step from green, one step from orange. And so it goes like, it develops a model that replicates that, but yellow is supposed to be two steps from blue. And actually the model developed is not 2 steps from blue, it's just 1, 2, 3 steps from blue. So it's not exactly the same model as the one developed originally, as the Newton's color model. It's a variation, but again, it's accepted by the social group in a way that the viscosity of the social group doesn't really change. Here we see the same simulation, but with 20 agents. And the learning agent is the one that is off the configuration, and you see the behavior is like trying to learn different models and testing different models and choosing what's the most adequate one. We are not going into the details of how we calibrate the Q-learning algorithm because you could customize here the different parameters to calibrate the best selection of models. But we did an experiment trying to assess what's the quality of the model, and this is a summary of our results. On the left, you see that this is from the perspective of the learning agent. That's the assessment of the learning model. How good is the color model that agent is developing? And essentially, it really depends on how many agents on the horizontal axis from 10 to 20. How many agents you interact with, and on the vertical axis, the tolerance to imperfect action. So the more tolerant are the people to a model, the more my perception of what I'm learning is higher. And also the larger number of agents I interact with, the quality of the model, from my point of view, from the agent's point of view, it's better. However, when you see then the behavior of that model from a third-person perspective, which is the visualization on the right, we are comparing both color models, how they are close to each other or far away from each other, how similar are the models, and we see like the reverse behavior. The more agents you interact with, the less similar the model to the agents. And the more tolerant the agents, the less similar the color model to the dominant model of the social groups. And we did an experiment trying to estimate the effect of introducing a learning agent in the social viscosity of a group. So we ran 2 batches of simulations, one of them without the learning agent and the other one with the learning agent. And we compare the social viscosity between the two batches for each one of the independent variables, in this case, the number of people, the number of actors or agents you interact with, and the tolerance. And we found that there are like statistical significant case that viscosity increases, and half of them shows that viscosity decreases. So there is not a conclusive tendency here. We know that it's an effect of learning, and the participation of learning agents in the social group has an effect on the viscosity that in some cases forces agents to adapt themselves more, in other cases reduce that adaptation. So we are like interested now in what happens if we have a split population. So let's say half of the agents have the Newton's color model, and the other half has a different color model. What's going to be the learning process? What's going to learn that agent? Is it going to do like a syncretism between the two models, or it's going to develop something new? Is it going to be equally acceptable? So we are in that stage. At this point, we are just running the simulations, and we want to make emphasis here, or show here. Again, I want to show this in this slide again. At that point, we see that there's no color wheel. We are showing that two different axes. Although we have two different color models, the agents find arrangements that are, in this case, represented in a linear fashion, but we run the simulation to represent them again in a color wheel. They find a way to arrange again in a specific order, but it's not favoring any of the two color models. It's like a combination of both. So we are exploring how the agents may learn color models in this like hybrid situation. So in some observations from these experiments, it's like the tolerance is to imperfect action is like really important in the learning process, and also in the consolidation of social viscosity. The higher the tolerance is really, it's more convenient for reducing the viscosity. But in the higher tolerant environments, the learning process is not as effective. And also the number of agents you interact with is also very relevant. Finally, we found that social viscosity could be a valuable proxy to assess the impact of learning agents in a collective. And we found that reinforcement learning, it's a promising area for the development of identity, or like study of identity, and or in general sense, learning models for social interaction in agent-based modeling. Now, we have some challenges, like in general terms, generating and selecting the best model from an infinite list of candidates, because, well, it's not really infinite, but it's a very large list of candidates, because permutations of agents, in this case, we have 20 agents, and you know that the permutation of 20 is a very long list, so computationally, it's very demanding. And but we want to understand the relation between the local reward of choosing a good model and the impact on the global viscosity, because choosing a good model not necessarily means that in some cases, hinders positive interactions, but it benefits the requirement of my own model. Thank you very much for your attention, and I'm happy to answer questions.
Thank you very much, Juan and Daniela. If there are any questions, please feel free to post them in the chat or raise your hand. I think we have time for a couple of questions.
I had a question.
Go ahead, Josh.
Well, at first I thought this was very, very intriguing work, and I was just wondering, could you imagine, so in my own work, I'm worrying about, we have these rule spaces, and we don't know really you don't really know how to say, is one rule close to another rule, but you're talking about a way of thinking of things, what colors are between another two colors, or which color is the neighbor of another color. And a color wheel is a kind of ordering. And I'm wondering, could you imagine a kind of rule wheel where instead of colors, they're behavioral rules, some small number of them, and some societies would order them in one way, and other societies would order them in, another way. And in a funny way, the agents generate their own rule wheel, right? I mean, there's an agreed proximity of behaviors. It's like, I don't know what they would be. I mean, go to the nude beach and walk into work or something. I don't know what, but I mean, the point is, can you imagine toying around with that analogy where instead of a color wheel, it's a kind of rule wheel, and what emerges is a cognitive map of how close different behaviors are to one another. And there could be reinforcement, right? If I leave the nude beach and walk into the police station, I might get in trouble, you know, or something like this. I have no idea what I'm talking about. I'm just asking. That I'm looking for ways to do this, and it struck me that this might be an intriguing way.
Well, thank you for the question. It's really something we have been wondering on how to translate this into like more general cases. Although the idea of colors is very abstract but easy to grasp. But we found that is one of the major challenges is to use order models. So here, there's something that is before and after, either by color or either by measurement. So we are dealing here with like conceptual spaces, and we need to think of conceptual spaces in terms of like something we can sort, organize, measure, and I don't think that all the rules are organizable that way. I mean, we need to develop a concept of how to convert a sequence of rules into something that has a hierarchical order.
Exactly right. I mean, it's kind of says we're not going to worry about assigning a distance, but maybe we can order them, and maybe in different worlds they're ordered in different ways, and that, you know, that could affect how the collective functions or how it interacts with other collectives. But yeah, I think it's very intriguing. I'd love to follow up. That's okay.
I found that perhaps some techniques of dimensionality reduction might help here. Like non-metric, this experiment is the color wheel experiment is the origin of non-metric multidimensional scaling. So I think that belongs to a family of like dimensionality reduction techniques that we may explore further in that space.
Nice. Thank you.
Thank you.
Thank you. Great discussion. All right, I think we're ready to move on to our